Okay, so good morning, everybody. It's my pleasure to introduce Ekaterina Leonova. She just obtained her master's degree in fundamental mathematics in St. Petersburg, Russia. Her main interests are algebraic number theory and functional analysis. She also has participated in a few mathematical competitions, including a first prize in the International Tournament of Young Mathematicians 2016. So I thank Ekaterina for her time. Today she will talk about Jacobi matrices and inverse spectral theory. So Katerina, thank you very much for being here.
Yeah. Nice to meet you all. So, right, today I'm going to talk about Jacobi matrices and inverse spectral theory as a part of functional analysis. So, what exactly is going to happen? I'm pretty sure everyone knows that what is like classical spectral theory, like we have a matrix and we want to know its eigenvalues. Usually we use it to solve some problem of matrix classification, but we might need eigenvalues of matrix for different reasons. And this problem is not like absolutely easy to solve, but there is like a known way how to do it, how to find eigenvalues, what to do with them. So there is a question, can we go backwards now? So if the eigenvalues of the matrix is given, what we can obtain, what information we can obtain about the matrix. So it's not so easy because first of all, we don't even have an injection if we have just like some amount of eigenvalues. If there are similar eigenvalues, we don't even know how the Jordan cells look because there might be like one big Jordan cell or there might be a lot of small Jordan cells. So we don't have an injection and we also don't have a surjection. No, we have a surjection, but one set of eigenvalues can correspond to like lots of matrices because we take like a Jordan cell and then we can multiply it from both sides and get like tons of different matrices. So probably we gotta do something to make this problem like a problem that at least has a solution, like a single one. So the easiest way to solve it is to not to work with all matrices. So usually what is done, people study Jacobi matrices. What is the Jacobi matrix? It's basically a symmetric three diagonal matrices. So everything except the main diagonal and the two above and under it are zeros. And it's also symmetric. Usually we have the coefficients an and bn in real numbers, and an is usually greater than 0. What are the main properties of these matrices? Why do we choose them? Well, first of all, Jacobi matrix is symmetric, so all eigenvalues are real and simple. So that one question that was about like the size of Jordan cells, it's solved already because all eigenvalues is simple, no problems with that. Secondly, these matrices don't come from nowhere. They are connected to some problems of physics. I'm not gonna talk about this one because first of all, it's not really what I'm talking about. And secondly, I don't really know a lot about this because it's more about physics. But if someone is interested, the code words are totalized. And third thing, very important thing, is that actually it's connected to some kind of problem in differential equations. So if we take a Schrodinger equation, you can see it here, the continuous case. And if you take the eigenvalue problem for a Jacobi matrix, you can see it on the right. They don't really look that similar. But the point is that a lot of spectral properties are the same. So the way eigenvalues are arranged and some of their properties, they are really similar. And we will use it in the future like a lot. So what was known about these matrices? First of all, we can consider the eigenvalues of this matrix. Of the Jacobi matrix, GP will be the Jacobi matrix of the size B. So what's the question? Can we uniquely recover a Jacobi matrix from its eigenvalues? Well, the answer is no. So what are the solutions? We can take more eigenvalues so that we know the result, or we can take a smaller amount of matrices. And actually, both of these solutions work. So now we are going to see how exactly they work. The first solution is to take another kind of eigenvalues. What are we going to do? We're going to take our matrix and remove the last row and the last column. And so this matrix will be called GP with a 1 on the downside. And we will denote its eigenvalues as tau n. So it was proved by Hofstadt in 1978 that if we take the set of eigenvalues plus these eigenvalues, the special ones, then we will have a bijection with a set of all Jacobi matrices with the coefficients AP greater than 0. What is the other solution? The other solution is take a smaller amount of matrices. We can take only bisymmetric matrices. Well, a square matrix is bisymmetric if it is symmetric about both its main diagonals. So we take like the first half, and then the second half is just like the same, but going backwards. So it was proved also in 1978, but by other people, De Boer and Group, that if we take bisymmetric matrices and just ordinary eigenvalues, then we will have a bijection. So a bisymmetric Jacobi matrix can be uniquely recovered from the set of its eigenvalues. So the question is, are these two solutions connected? And it turns out that this is actually one way to approach two ways to approach one solution. But it was known in the continuous case. So if we take this equation, but if we take not any function q, but the one with the support on 0, 1, or well, it can be any finite support, just it's easier to take 0, 1. And if we take an even extension of q, then we will find out that the eigenvalues of the even extension are both the eigenvalues and the special eigenvalues of the initial equation. What is the logical question is, what is the special eigenvalues in this case? Because if we have some function, we can just like delete a row and a column from it. No way. But this is for, I think that everyone who knows about the differential equations, the eigenvalues problems, it usually goes with some conditions like a Dirichlet condition and Newman condition. So the numbers nu, they are going with a Dirichlet condition. So the function y is gonna be equal to 0 at 1 and at 0. And this tau goes for mixed eigenvalues, which means that we have 0 on the one side of the function y and 0 of its derivative on the another side. So that's what this number is in this case. So we see that if we take an even extension, that then its eigenvalues cover both of these eigenvalues. But okay, then we need an even extension of a Jacobi matrix. We gotta try to do the same with the Jacobi matrix. Maybe it works. But then there is a problem because we don't really know what is an even extension of a matrix. I'm pretty sure you didn't hear about this one. We are not going to define it for any matrix, of course, but we will talk about the Jacobi matrix. So if we have a matrix, what we can do, how we can make an even extension? Well, the first option is just we take a matrix, then we take it again, like do it like backwards, and then take them together like this, option 1. But then we don't really know one element, which goes after Bn and then before the copy of the Bn. We don't know what it is. So we will have to somehow find it to make it work. And also there is a problem because this thing, it will be of a size 2p. And so it will have 2p eigenvalues. But if we want this to happen, then this is a set of p eigenvalues, and this is a set of p minus 1 eigenvalues. So we have 2p minus 1 eigenvalues in total, and we can't have it here. So this option doesn't work. Okay, so then we have an option 2. We can do the same, but we can move the matrices a little bit so that it won't have 2 copies of Bn. It will only have 1 Bn. So maybe it has just a p minus 1 around it, but maybe it doesn't, because like we just took 2 matrices and like they kind of collided. So maybe it changes the coefficient. So what did we do? We just wanted to find such coefficient so that this happens. And the answer is that. So it turns out that we have to divide the AP minus 1 by square root of 2. So if we take this matrix, then the spectral properties will be the same as in the continuous case. So if we take the eigenvalues of this matrix, some of them will be the eigenvalues of the initial matrix, JP, and some of them will be the eigenvalues of the matrix JP1, matrix JP without the last row and last column. So this is the result. And also this matrix is unique. So it was already what I've been doing with my scientific advisor. We found this matrix, and we found out that if we want to have this property, then there is a single matrix with this one, a single logical matrix, of course. So if we want to talk about the spectral properties, this is what should be called an even extension of matrix, even though it doesn't absolutely look like a right solution, it actually is. So, okay, what can we do now? We can also consider a periodic matrix. So I didn't say, so this way, if we consider this matrix, we find out that these 2 solutions that I was talking about earlier, that this is actually one solution, because we can recover a matrix from this one, or we can make it bigger and then recover it from this one. So it's actually the same. Right, so what do we do next? Next, we can consider a periodic matrix, any periodic matrix. And well, of course, if we take a periodic matrix, we can consider its eigenvalues. It's not what we usually do at like our first years of study in the university, because we only talk about metrics that are small, that have a size. And of course, if we want to try to find some kind of eigenvalues of a periodic matrix, might be complicated. We don't really know how it works. But we will consider a simple case. We will consider periodic and antiperiodic eigenvalues. So we want to find eigenvectors that will be first periodic, so with the same size. So we have this matrix, it's periodic because we have AM equals A0. And we want to have eigenvectors that are also periodic. Then this problem of finding these vectors, it will, we can make it a finite condition problem, because we can just consider a part of this matrix and move this A0 to somewhere over here, and then take this AM to somewhere over there, and we will have one matrix. And since the eigenvectors are also periodic, just like the matrix itself, it will work. So it will be, again, something simple, something finite dimensional, we know how to work with. And also we want to consider antiperiodic eigenvalues. It's the same thing, but we want an eigenvector to be like there's something from 1 to m. And then for the next m points, we want it to be like minus what was before that, and then minus again. So it will be like 2m periodic and antiperiodic every m steps. So we also can make a finite dimensional problem from this. We can again consider this part, and to take an A0, take a minus m0 and move it here, and then take AM, turn it into minus AM and move it there. and it will be the matrix that will give us the eigenvalues we need. They will be denoted as lambda n from 0 to m, but since we will have 2m eigenvalues in total, not like 2m plus 2, we have to say that there will be like from n to minus, for n from 1 to minus m minus 1, there will be 2 eigenvalues, lambda plus and lambda minus, and for lambda 0 and lambda m, there will be only one of them. Okay, so, and it turns out that we have this, that like lambda 0 is always going with a plus, and it's less than lambda 1 minus. It can be equal to lambda 1 plus, but it's smaller than lambda 2 minus. And it goes like this until we have lambda m minus. It goes without a plus because it's a single one. So what do we have again in the continuous case? Like, I have to say that all the results in the continuous case that I've been talking about, they are old. Like, it's these results, it's 1960 something. So it's they were discovered even before these simple things about matrices, about Jacobi matrices that I've been talking about, because everyone were more interested about differential equations than matrices. But now we actually need matrices a lot because it's connected with all the discrete things, with all the computer things, with all the things that have like steps. And so now this is the important part. So now we have to study this one. So there is another pretty old result. If we take even periodic functions, like if we take not the matrix, but an even function, we can also find these eigenvalues. They have to be with an integral equal to 0. And now we have a more complicated spectral data. It's not just like some kind of eigenvalues, it's a sequence of differences between lambda n plus and lambda n minus. So we don't really care about these two guys. We don't need them. We don't need them. And we will have a bijection then. Well, now we want to see, like, all the previous things, they were pretty similar in the discrete case and in the continuous case. The only thing is that in the continuous case, everything is infinite. So there's an infinite amount of eigenvalues, infinite amount of other things. But what do we have here? So in 2006, Evgeny Karateyev, my scientific advisor, built some kind of a gap length mapping. It is some kind of bijection, but it's not just a bijection, it's also an analytic one. So we can see how it changes with the change of the matrix, because it's smooth and all. But it was made not for like some kind of even matrices. It was made for all periodic Jacobi matrices. And there he needed, I don't put this mapping here because it needs like a page of explanation, because it's not only the periodic eigenvalues, it needs one of those two eigenvalues I was talking earlier. It needs some special eigenvalues, and it needs some more complicated spectral data. It needs some special, needs some signs, needs some square roots and other things. So it's there, but it's not really useful because it's too complicated. And so what was done in 2020, we were able to find that this bijection in terms of gap lengths, the thing is that this space between lambda plus and lambda minus, like this one, is usually called a gap. So it can be small, it can be big, it can be like size of 0. It's usually called a gap. So we have this kind of gap length. So we also know that if we take, it's not just, it has to be like a sum of bn got to be equal to 0 and a sum of an got to be equal to 1, because all ans are greater than 0. So we can have something like this. Of course, we have the sum equal to 1. Then we have a similar bijection, and we can also have some estimates for the size of a squared plus b squared, usually this thing, this q thing and the AB thing in terms of matrices is called a potential. So we can estimate the size of the potential in terms of gap length. So, and now we can try to put it all together. Remember what was happening in the beginning and connect it with the periodic matrices too, because we just want to make one big connection to see that it all connects. How? So now we need 4 kinds of eigenvalues. Well, we need the eigenvalues of the matrix GP, the initial matrix. We need these eigenvalues. We already know them. It's the last row and the last column deleted. We can also delete the first row and the first column. It makes sense. And then we will have these numbers. And we also can do both. So we can delete the first row and column and the last row and column. Like, because in the continuous case, we have a Newman problem. It will be an analog of this, and we have a Dirichlet problem, this, and these two are called mixed eigenvalues because we have one of the Dirichlet and Newman problem on the one side and another one on the other side, so we can switch places. So there are 2 of those. Actually, we also have this, so we kind of know how they are arranged on the line, these eigenvalues. Right. And what we do, so we know how to build an even extension, and so it makes sense if we want to build a periodic matrix, we can build it using what we already know how to do. So like, first of all, we took our matrix, then we made these things, so we put 2 matrices together, and then we can do the same around the B1. We can put it with another matrix, and we do it like infinitely many times. So we have a periodic matrix now. Every piece of it is bisymmetric, or even, how we can call it now, and we have a round of these guys divided by a square root of 2 around B and B1. Great. What can we do here? It turns out that this matrix has a lot of interesting spectral properties. For example, we know where all of these eigenvalues, the periodic and antiperiodic eigenvalues, are located. They are located exactly in these 4 spectra that we chose earlier. So all of them are, like, the even ones are exactly the Dirichlet or Newman eigenvalues, like the initial matrix and matrix with 2 rows and 2 columns deleted. And all of the odd ones are the ones with the mixed eigenvalues, with 1 row and 1 column deleted. So now we can recover even periodic matrix from this eigenvalue. So starting from finite matrices, we can move to bigger matrices just using bigger symmetric matrices, bisymmetric matrices, using the even extension property. And then we can take a periodic extension of this one, because we already know how to do it. And then we can connect the infinite matrices and the periodic matrices. It's also pretty useful because I'm not talking about these results now, but it seems that I will have time in the end, so I can give like an outline. But the point is that usually we know much more things in a periodic case than in a finite case. And now for every finite matrix, we can build periodic ones. So we can study finite matrices now using things that we know about periodic ones. And there are like a lot of things. So, and yeah, we can also recover periodic matrices from the eigenvalues easily. But this is not the main result. The main result is what I've started to talk about before. Like we had this kind of gap length mapping, but we can also now move it to the finite case. So what do? We can define a four-spectrum mapping. This space, HP minus 1, HP1, it's nothing complicated. It's just we want our coefficients to be like I was talking about, like we want the sum of A's be equal to 1, and we want the sum of B's be equal to 0, so nothing special. And we will have a mapping. So from Q, the potential, which is basically A and B, we'll move to the differences between these eigenvalues and these eigenvalues. And this is basically a gap length mapping that I was talking about earlier, but used in a finite case. So what do we have here? The result of what we've been doing is this theorem. The four-spectrum mapping is actually a real analytic isomorphism. So it helps us in this way that we can study how the matrix changes using the way its eigenvalues change, because now we know that there's like an analyticity. So we can see that if this change is small, then that change is also small, which is pretty useful, because sometimes it might happen so the eigenvalues, like these two, might change a lot, but the difference might not change a lot. So there are some special cases that are pretty interesting. And we have an estimate. So we actually, it turns out that we can find out how big the coefficients of our matrix are using these gap lengths. Or we can actually do it like, the interesting thing is that here you can see, just like we didn't use these two guys. So there are two estimates. One is based on the four-spectrum mapping that does not use mu0 and mu p minus 1, and another one is based on based only on them. So these two estimates are used for two different cases, like when the spectrum is like small and everything is close to each other, then it's better to use the big difference. And when the spectrum is pretty big, then it's better to use this thing. So yeah, and it was pretty fast, so I can talk about what else can be done. First of all, one of the interesting results is that we can actually recover our matrix GP from a mix of four spectra. So I can go back here, and it was in the beginning that there is like a knowledge result, 1978, that we can take these eigenvalues and these eigenvalues, and then we know the Jacobi matrix. But the thing is that these eigenvalues and these eigenvalues are similar in some special way, but there is like a smaller amount of those. So we start from 1 and end with p minus 1, so p minus 2. So we can't get rid of those two, but we can say that we know not all of these guys, but we know, like, for example, half of these guys and another half of those. Or like we know mu0 and mu2 and mu2 and mu3 and mu4 and like this. And just same thing here. So they are also connected in some way. So we can take like some from here, some from there. Like for every number we got to take one here or there, but doesn't matter. And we will still be able to find a matrix JP. So I think that this is pretty interesting. And also this mapping actually will be also continuous. There won't be like analyticity, but it will be continuous. So what is other thing? The other thing that it's like, I wasn't going to talk about this because this is for some kind of further study. It's more complicated. We can consider infinite matrices now that are not periodic or something, but they have some kind of finite support. something like a matrix GP, and then after some number, it goes like zeros on the man diagonal and ones around it. And we can consider eigenvalues of this matrix. And this is called like a resonance problem. It's what I've been doing lately, and it's usually interesting how we can go from like simple questions to some kind of complicated maths. Like we ask something like about x to the nth power plus y to the nth power equals z to the nth power, and we have some great science behind it. And here also, if we want to talk about how these guys are located, we need some kind of complex analysis, for example, and a lot of study of polynomials. So it's also pretty interesting. And what is the point of this? One of the main point of this is we have another way to look at lots of number sequences, because we can represent them as eigenvalues, or like simple eigenvalues, or like some complicated eigenvalues of different matrices. Like, for example, if we have a JP, like a matrix, with the coefficients, with all coefficients like this, like it's finite, it's simple, but all b ends 0 and all a ends are 1s, except for the first one and the last one. So it goes with a square root of 2, so that it will be only zeros and ones if we take a periodic extension. So if we consider this matrix, then for example, we will have the characteristic polynomials will be basically Chebyshev polynomials of the second kind. If I think some of you might have heard of that. So its roots will be some kind of trigonometric functions like cosine and sinuses of things, and we can also find some relations between them about like the way they're placed. And I mean, we know a lot of things about how trigonometric stuff is placed on the real line. It's not so hard, not some science, but it's a simple case. A ends are ones and b ends are zeros. So if we take something more interesting, like for example, I want to try taking something with like prime numbers, then we might find some interesting results. So I think this is mostly what I wanted to say. So I can thank you for your attention and wait for your questions if you have some.
Thank you very much, Ekaterina.